The title of my talk is Design of Experiments for Simulation Modeling. I actually have about 250 PowerPoint slides, so obviously we're only going to be able to do a relatively small part of that, like 240 slides maybe. I'm just kidding. So here is a very brief outline. We're going to have an introduction, not shocking, and we'll talk about using design of experiments for factor screening, finding the factors that are the most important, and then we'll talk fairly briefly about developing a meta model or response surface, which would be a regression equation for predicting the value of the response for values of the parameters that we didn't actually simulate. So anyway, here we go with the introduction. Let's suppose that we have k factors, at least 2, otherwise it wouldn't be very interesting, of interest for a simulation model. Factors can be quantitative or qualitative. We'll see examples of what factors might be in a while. And the major goal of design of experiments is to determine which factors have the greatest effect on a response, and to do so with the least amount of simulating. And this is often called factor screening. Other goals, which we'll talk about briefly, are to develop a meta model, which is usually in the form of a regression equation, based on the important factors that can be used to predict the model response for system configurations or factor levels that weren't actually simulated, maybe due to cost constraints. And also, you can potentially use this meta model to find the system configuration that optimizes the model response. And I'll give you a little idea of that as well. Okay, going to factor screening. Suppose we want to get an estimate of how each factor affects a response. We might also want to determine if the factors interact with each other, i.e. the effect of one factor in response depends on the level of another factor. Now, one way to measure the effect of a particular factor would be to fix the levels or values of the other k-1 factors and to make simulation runs for 2 or more levels of the factor of interest to see what effect changing factor 1 has in the response. Once we do that, we would go on to factor 2, set the levels of the other k-1 factors, run the simulation for several values of factor 2, and see what impact that has on the simulation response. And this is called the one factor at a time, or OFAT method. And unfortunately, this approach is very ubiquitous and in general not the right thing to do. It's inefficient in that the estimates of the effect of a factor have unnecessarily large variability, and also this one factor at a time approach cannot measure interactions. Matter of fact, it assumes no interactions when in fact many simulation models do have interactions. And so one factor time is definitely something you shouldn't be doing, even though one person actually said they thought it was a scientific method. Okay, a better approach, which we'll be talking about here, is called a 2 to the k factorial design. And it requires that we choose just 2 levels for each factor and then simulate each of the possible factor level combinations, which are called design points. So if we had k factors, each of which are run at 2 levels, we would have 2 times 2 down to a product of k different 2's, which would be 2 to the k different factor combinations. We would run our simulation at. Anything with a red star is supposed to be somewhat important. Let's assume temporarily, for sake of discussion, that the response is proximally a linear or at least monotonic function over the range of the factor levels chosen. And let's look at figure 1 here. And let's say we have a particular factor and we see minus and plus. The minus is the, say, lower numerical value for the factor, the plus is the larger numerical value of the factor. And ideally, we would hope that as we move the factor over the range minus the plus, that the response would increase in a linear manner, either with a positive slope or negative slope. In general, though, we will be okay if we have monotonicity as indicated by the green line. One thing we don't want to have, though, is a non-monotonic response as we move over the range. Because if we simulated the simulation, or we run our simulation at the minus level and our plus level, and we get approximately the same response values, we may conclude that moving the factor over to range has no real effect on the response. Let me go back one slide and see if there's anything I missed there. So if it is linear over the range, then we can get a good characterization of the response by just simulating at two levels. And I might mention that there are ways to check this linearity assumption. The levels should be chosen in consultation with subject matter experts. As we suggested, we will code one level of a factor by a minus sign and the other level of the factor by a plus sign. The levels should be far enough apart so that we would expect to see a difference in the response, but not so far apart that a nonsensical configuration is obtained. The form of the experiment can be compactly represented by the design matrix, which is shown in table 1 below in the case of 3 factors. And let's see what it looks like. We're going to have, since it's 2 to the 3, we're going to have 8 different design points. And the way this is set up, if you were doing it kind of by hand, is first we look at factor 1, and you notice that we go minus, plus, etc. And then when we go to factor 2, we have 2 minuses, 2 pluses, and so forth. And then when we go to factor 3, we have 4 minuses and 4 pluses. And this actually gives us our 8 factor level combinations. And so the first thing we would do would be to run our simulation with each of the factors at its minus level. And then we'd get a response out of the simulation, R sub 1. And then we'd run the simulation, obviously, with factor 1 at its plus level and factors 2 and 3 at their minus levels, and we get a response out R sub 2. Now, one of the major concepts of when you're talking about design of experiments is what is called the main effect. And the main effect of factor J, which we'll denote by E sub J, is the difference between the average response when factor J is at its plus level and the average response when it is at its minus level. And this will be clearer by means of an example. So let's go back to the case of 3 factors, and let's see how E1 is computed. And so it says the average response when factor 1 is at its plus level. And if we look here at column 2, I guess it is, we see that factor 1 is at its plus level for factor combinations 2, 4, 6, and 8. So we take those 4 response values, we add them up and divide by 4. We get the average response value when factor 1 is at its plus level. And then by process of elimination over here, we have the average response when factor 1 is at its minus level. And as we said, the main effect of factor 1 is the difference of those 2 averages. Now we can rewrite that first expression there by getting a common denominator of 4 and arranging the terms in increasing order of the subscript. And so we're going to get minus R1 plus R2, etc. Now, is there some simple way that we can actually get that latter formula? And the answer is yes. We can take this column of, you could think of this as minus 1 plus 1 and so forth. And we can multiply this column of minus 1s and plus 1s times the response column, row by row, and then take the sum. What we're doing in mathematical terms is we're taking the dot or scalar product of the 2 vectors, the factor 1 column and the response column. And I guess I've already said that in the first paragraph here. on this page. And maybe you would like to see a geometric interpretation of this definition of E sub 1. And E sub 1 is equal to the average of the 4 responses on the right face of the cube minus the average of the 4 responses on the left side of the cube. So here is our cube. If we look at factor 1, it goes from its minus level to its plus level. Factor 2 goes from its minus level to its plus level. Factor 3 goes from minus to plus. Here is the right face of the cube. You notice I put a plus sign there because we're looking at 4 design points for which factor 1 is at its plus level. And we have 2, 4, 6, and 8 again. So we take the average response over those 4, indicated by being green, minus the average response of the 4 responses or design points on the left face of the cube. So it's minus that average. Now, one caveat of design of experiments is the interpretation of a main effect. Let's suppose that the numerical value of the main effect of a factor happened to come out plus 10. Then some people might believe that if we move that factor from its minus level to its plus level, that in fact the response goes up by 10 units. But it turns out that that is not in general true. It will only be true if there are no interactions, as we will discuss briefly later on. Now, the main effects measure the average change in the response due to a change in an individual factor. It could be, though, that the effect of factor J1 depends on the level of some other factor, let's say J sub 2, in which case these 2 factors are said to interact. So let us define now the 2-factor interaction effect between factors J1 and J2, which we will denote, and this is not totally standard notation, E sub J1, J2. And similar to the main effect definition, this is the difference between the average response when factors J1 and J2 are at the same level, say both plus or both minus, and the average response when they are at opposite levels. And once again, this will be easier to see with an example. Another name for this is the J1 cross J2 interaction. And it turns out we could also define and say 3-factor interactions. We could actually visualize that, and we could go all the way up to a K-factor interaction effect. So let's go back to our example of K equals 3 factors. And let's look at, as an example, the interaction effect between factors 1 and 2. And what did it say? The average response when factors 1 and 2 are at the same level. And if we come down here, we can see factor 1 for design point 1, we see factor 1 and factor 2 at the same levels, namely both minus. And then if we come over here to design point 4, we see factors 1 and 2 once again are at the same level, in this case plus. And so altogether we'll have 1, 4, 5, and 8. We add those together, divide by 4, we get the average response when factors 1 and 2 are at the same level. And then once again, by process of elimination here, we have the average response when factors 1 and 2 are opposite levels, minus plus or plus minus. Once again, we can rewrite this expression using a common denominator 4, arranging the terms in increasing order of the subscript. Now, how do we get that latter expression? Well, once again, you can think of factor 1, the factor 1 and factor 2 columns as being minus 1s and plus 1s. So we're going to take the dot or scalar product of columns 1 and 2. And then that product we will multiply by the response column row by row and sum that up. So for example, how do we get this here? Well, we're going to take minus times minus, which is a plus, so we'll have a plus R1. And then coming down here to design point 2, we will take plus times minus, which is a minus, so we will have minus R2 and so forth. Okay, let's look at the geometric interpretation, similar to what we did before. A geometric interpretation of the definition of the 1×2 interaction effect is given in the figure that will follow. And maybe the simplest thing to do is just look at the picture directly. So once again, here we see R cubed with factor 1, factor 2, factor 3. And if we look at the plane slicing through this cubed, namely the green plane, and once again we have 4 responses, 1, 5, 8, and 4. And if we take the average of those 4 responses, and by the way, for each of the responses on that plane, the 2 factors are at the same level up here. And then we look at the plane that's perpendicular to the original plane, namely the red plane, and we take the average response over the 4 corners, namely responses 2, 3, 6, and 7. And those 4 responses correspond to design points where the factors are at opposite levels. So once again, we're taking the average response for the 4 design points where the points are at opposite levels, the factors in particular, minus the average response when the factor levels are opposite. Okay, our first example will be a periodic review inventory system. Inventory systems are something that have been widely simulated historically, maybe in the military, wanting to know how many spare parts to have for each different, say, part number, maybe an automotive supplier wanting to know how many copies of each particular spare part they need and so forth. Now this is an academic example for simplicity, but it will have many of the aspects of a real inventory problem, a real world inventory problem. We have 3 sources of randomness here. First of all, we have inter-arrival times, which I'll denote by A sub I. This is the time between the I minus first and ith arrivals. And we're going to assume that these inter-arrival times have a certain probability distribution that tilde their means distributed as. And we're going to assume that inter-arrival times are exponentially distributed. Exponential is widely used for inter-arrival times with a mean of 0.1 month. On average, about every 3 days, a customer will arrive and want to buy this company's product. The second source of randomness is demand sizes. And this is going to be a discrete random variable. Seems like we're going very fast here in terms of covering PowerPoint slides. So demand size I will denote by D sub I. And this is the number of items that a customer wants to buy when it arrives. And the demand size can be 1, 2, 3, or 4 items. And those values occur with probabilities a sixth, a third, and sixth. You notice obviously that the probabilities add to 1. Now this is a periodic review inventory system. Let's say the company reviews their inventory level at the beginning of each month to decide whether to order any items from its supplier. And we will use the notation capital I sub K to be the inventory level at the beginning of month K. If it's plus, then the company has items in their warehouse. If it's minus, then the company has nothing in its warehouse but owes items to customers that previously demanded them. Now, quite often in the real world, people use what is called a little s, big S inventory policy to decide whether to order, and if so, how much. Little s is called the reorder point. And for lack of a better name, we'll call big S the target amount or the order up to amount. And the way a little s, big S inventory policy works is that at the beginning of the month you check your inventory level, and if I sub k is less than this reorder point, little s, then we're going to place an order to your supplier. And the amount that we order will denote by little z, and the amount of the order will be where we want to be, capital S, minus our current inventory level, I sub k. And if we place an order for little z items, we incur an ordering cost, capital O sub k, which is linear. First of all, there's a $32 setup cost, regardless of the size of the order, and then we have an incremental cost of $3 for each item we order. Because of the setup cost, we don't want to be ordering, any more than necessary. Now, if I sub k is at least as big as little s, then we will place no order, and our ordering cost for the kth month will be 0. Our third source of randomness is the delivery lag or lead time, capital L. And this is the time from when the company places an order to the supplier until the order actually arrives at the company. And here we're going to assume that the delivery lag is distributed as a uniform random variable on the interval 0.5 to 1 month. Every value between 0.5 and 1 month is equally likely. Now in the real world, it's likely to be uniform over that range, but for simplicity, sake of discussion, we'll assume uniform is correct. Now, if the demand for a particular customer is greater than the current inventory level, for example, maybe you have 2 items in your warehouse, the customer comes in and wants to buy 4. Okay, what we're going to do is we're going to make the assumption of backlogging. You give the customer the 2 items that you have, and then you backlog or keep track of the 2 items that you still owe the customer. And those 2 backlog items will be satisfied when you get an order from your supplier. And this actually makes your inventory level go to -2 then. Now, so far we've talked about ordering cost. Most inventory problems will also have a holding cost, which will denote by I sub k in month k. And it's $1 times the average number of items physically in inventory, which will be non-negative. So if in your warehouse you have 5 items, you have 5 items physically in your warehouse. If your inventory level is -2 because you owe customers 2 items, then your inventory level is physically 0. And so the holding cost in month K will be $1 times the average number of items physically in inventory. Here we're also going to have a shortage cost. Not all inventory problems may have one. Shortage cost denoted by S sub k in month K, and it will be $5 times the average shortage level, which will be non-negative in month K. And if you have, say, 3 items in your warehouse, you have no shortage, whereas if the inventory level, say, is -3, then you have a shortage of 3 items. The total cost, C sub k, of operating your inventory system in month K is given by C sub k, which is the sum of your 3 individual costs, being ordering, holding, and shortage. And the response of interest for our simulation model, here for some reason I used a 10-year planning horizon, 120 months, and we're looking at the average value of C sub k over this 120-month planning horizon, and the initial inventory level for our company is 60. Okay, now instead of looking at the factors little s and big S it turns out we have to do something slightly different to set up our coding chart here. And what we're going to do is we're going to look at little s and we're going to look at little d. Little d is defined to be big S minus little s. If you know little s and you know little d, obviously you will know little s and big S. So the two parameterizations are equivalent. And what we will choose here, and we're not going to, since this is a made-up problem, we're not going to really worry about how we got these particular levels for our two factors, a little s and a little d. What we're going to look at here in our 2-to-the-2 design is little s at the levels 20 and 60, which you notice are 40 apart, and little d at levels 10 and 50, which is also 40 apart. In general, it is not necessary to have the two differences in levels to be equal, in this case 40. And you might ask, why do we parameterize things as little s and little d rather than the more obvious little s and big S? Well, let's suppose that this little d here was in fact big S. Then we could have a combination of little s equals 20 and big S equals 10. So if our inventory level, say, was 19, which is less than little s, the cutoff level there, so if our inventory level is 19 less than 20, then that would say that we're going to order up to 10, which of course makes no sense. When we actually do our simulation, we will be using little s and big S. But for the purposes of our coding chart, we're using little s and little d. And we went off and simulated these four-factor combinations. And we see our design matrix here, our four design points. If we look at little s and little d, in fact, it's the way we talked about before. Little s goes minus, plus, minus, plus, and then little d goes minus, minus, and plus, plus. We can take the dot or scalar product of those two columns and we get the s cross d column. And that will turn out to be, we multiply minus times minus, we get plus. Design point 2, if we multiply plus times minus, we get minus. So we're going to run our simulation at those four design points or combinations. And what comes out of the simulation are these four response values. 144.16 is the average cost over 120 months when we run our simulation with little s at level 20 and little d at level 10. Now, we can compute our main effects. And to get the main effect of little s, all we're doing is taking the column of signs in the little s column, multiplying it by the column of responses, and we're going to end up with $13.68. And if we can interpret that literally, this would say that if we move little s from its 20 level to its 60 level, we would expect average cost to go up by about $13.68, so that the smaller value of little s is superior, gives us a smaller average cost. And then going down to little d, we get minus $10.84. So if we could interpret this literally, the main effect of little d, that would say that if we move little d from its 10 level to its 50 level, we would expect the average cost per month to go down by about $10.84. So it would appear that the larger value of little d, namely 50, will result in a smaller average cost. If we go down now and compute the S cross D interaction effect, we get $13.34. And the fact that it's non-zero, we have an interaction, says we have an interaction, which means that we cannot really interpret the main effects literally. More discussion is necessary. Now the responses, namely the average costs over 120 months are random variables because we have 3 random variables driving the simulation. So the R's, which are computed from the input random variables, are also random. To determine whether the effects are statistically significant, which is a main concept in statistics, albeit an overly emphasized one, as opposed to being explainable by random fluctuation. We can replicate the whole design n times to obtain n IID values of each effect. IID means independent and identically distributed. This is, and another name for this would be a random sample. These are the fundamental assumptions of virtually any standard statistical technique like confidence intervals, hypothesis tests. What we're doing here is something you will not find in a standard design of experiment text. This idea was somehow developed or thought of by the former co-author of my book for the first 3 editions, David Kelton. And so then we're going to have, what we can do is we can use these to construct confidence intervals for the expected effects. And let's see mathematically what I mean by this. Let E sub j sub I be the observed effect of factor j on replication I. And then we can take the usual sample mean based on our n replicates right here. So once again, we're looking at factor j, and I is the replication number, and we're going to take the average mean effect of factor j across the n replications, the usual sample mean from statistics. And in a similar manner, we can get the usual sample variance, which is given by that formula, where if you divide by n minus 1, you get an unbiased estimator. And then we get our standard T confidence interval from statistics, which is the one that's usually recommended. An approximate 100 times 1 minus alpha % confidence interval for the expected or mean effect. E of E sub j is given by the standard formula. For example, if alpha was 0.05, we'd be going after a 95% confidence interval, which is standard in statistics. If alpha was 0.1, we'd be going after a 90% confidence interval, which is somewhat widely used in simulation itself. And if we look at our confidence interval formula here, the center of the confidence interval is the sample mean. This thing right here is called the half-length of the confidence interval. And you see right here the sample variance divided by n. That's actually an unbiased estimator of the variance of that sample mean. We take the square root of that. That's called the standard error of the sample mean. And we're going to multiply that by a t critical point with n minus 1 degrees of freedom because we have n independent replicates. And I don't think I actually showed the picture here because of lack of time, but that is the t critical point with n minus 1 degrees of freedom, leaving alpha over 2 of the area in the right tail. And you can look that up in a table, and any statistics book or Excel can compute that for you. Now it turns out that confidence intervals are in some sense equivalent to doing a hypothesis test. You might, for example, learn about doing a T hypothesis test where you want to test a null hypothesis H sub 0 that the expected mean effect of factor J is 0. But it turns out that whether that is accepted or rejected, so to speak, is equivalent to looking at the confidence interval. If the confidence interval for the expected main effect of factor J does not contain 0, then we conclude that the effect is statistically significant. The confidence interval doesn't contain 0, that's equivalent to rejecting the null hypothesis. If the confidence interval contains 0, that's equivalent to not rejecting the null hypothesis. But I would claim that confidence intervals are really more useful in general, because not only does the confidence interval give you the same information as the hypothesis test, but it gives you a measure or range in which the true expected mean effect of factor J will fall, which the hypothesis test does not give you. Now, if you look at most statistical books, or let's say a book in design experiments, statistical significance is determined using what's called analysis of variance, or ANOVA. And it would probably be pretty difficult to take a basic statistics course without studying analysis of variance. It actually has many uses in design of experiments, regression analysis, and other places. And if you were to use analysis of variance to determine statistical significance, it assumes that the response has the same population variance for each design point. Homogeneity of variances. This is a common assumption through much of statistics. But as we're going to see in the context of simulation, this is not only bad, but it's generally a dreadful assumption, which calls into question the use of analysis of variance as found in standard design of experiments texts. Okay, we're going to go back to our inventory problem. Up to now, we only had one replicate at each of the 4 design points. If you're doing a simulation, you should know you never want to run your simulation for a particular set of input variables or factor levels one time. You want to make multiple replications using different random numbers, which is easy to do, say, in ExtendSim. And so what we're going to do now is we're going to take the inventory problem, and rather than having one replicate at each of the 4 design points, now we're going to have 10 replicates. We're going to make 10 replications at each of the 4 design points. So altogether, we're going to be making 40 replications of our simulation model. And before we look at the main effects or interaction effect, we're going to look at summary statistics. And here we see them. So for example, one of the design points is running our simulation with little s equals 20 and little d equals 10, which is equivalent to having big S having a value of 30. And we're running that design point 10 times, and we're going to get a response value for each of the 10 replicates, and we take the average of those 10 responses, and we get an average cost of $135.71. We can also take the usual sample variance. It comes out to be 22.24. Then we could go down, for example, and make 10 replicates, which we did, at little s equals 60, little d equals 10, which means big S equals 70. We get an average response across the 10 replicates of 143.94. And we can do this for each of the 4 design points, getting a sample mean and a sample variance. And if we look at those sample variances, we see that they go from a minimum of 1.6 up to 22.24, and that is a ratio of 14 to 1, whereas the assumption underlying analysis of variance is that those variances should be roughly the same. Now we'll actually go and look at the effect estimates. Now, what we're going to look at here, which might seem kind of strange. Or maybe I should say it this way. Using 96 2/3% confidence intervals should be obvious to the most casual observer, jokingly speaking. We're going to have three confidence intervals, one for the expected mean effect of little s, one for the expected mean effect of little d, and one for the expected interaction effect between factors s and d. If, for example, we made them at least, or excuse me, if we made each of them at level 90%, the overall confidence level is not 90%. All we can really claim is that it's at least 70% that each of the three confidence intervals contains its respective expected effect. Now, there is something called the Bonferroni inequality, which I don't have time to go over. But it turns out that if we make each of the three confidence intervals 96 2/3, which means that each of the three alphas are 3 1/3, 3 times 3 1/3 is 10. And 100% minus 10% will give us 90%. So if we make each of them at level 96 2/3, the overall confidence level will be at level 90%. And if we look at those three confidence intervals, you notice that none of the three contains 0. The confidence interval, and I didn't really explain this as well as I should have before, the lower confidence of the endpoint in the case of factor S is 18.47 minus 2.58, and the upper confidence level is 18.47 plus 2.58. And that confidence interval does not contain 0. So the mean effect of little s is statistically significant. And we see that all three effects are statistically significant. Now, in statistics, we make a big deal about statistically significant, but unfortunately, statistical significance depends on the number of replications. If we had enough replications, the half-length of any one of those confidence intervals would get smaller and smaller and smaller. And let's see, this is coming out the way I want. Let me just leave it at statistical significance depends on the number of replications. If we make enough replications, we will always have, in general, the confidence interval not containing 0, so we will get statistical significance. I don't know why I didn't get that out the first time. So if we make enough replications, and if the effect has any impact at all, we will get statistical significance eventually. And I might mention, by the way, that if you want the half-length to be half as big, you will need approximately 4 times as many replications. So in this case here we have 10. If we went up to 40 replications, our first half-length would go down to about 1.259. Moving over here to page 42, slide 42. Okay, in figures 4 and 5, we give what are called mean effect plots for little s and d. And we just look at them here. So here we see little s, whose range goes from 20 to 60. Up here we have average cost. And at 20 here, we have an average cost of 127.58. And at little s equals 60, we have 146.06. Now, where did those numbers come from? Well, if we go back over here and we look at little s equals 20, which occurs for design points 1 and 3, we get 135.71 and 119.45. The sum of those two is roughly 255. And if we divide by 2, we get, let's see, 255, 127.25. And that's where that number there comes from. So if we could interpret the mean effect plots linearly, we would expect the average cost to increase by about 18.5 when we move little s from 20 to 60, as we said before, and to decrease by about $6 when we move d from 10 to 50. But this is something that is not completely understood, which I briefly mentioned for a caveat. Since there is, in fact, here a significant interaction between S and D, these mean effects are actually of limited value, as we're going to discuss further. So we go over here to page 45. And in figure 6, we're going to give an interaction plot for little s and little d, where the presence of a significant interaction is indicated by the non-parallel lines. So once again, we have little s going from 20 to 60, and we have two different lines. The top line here corresponds to d equals 10. If we move little d, if we have little d equals 10, and we move little s from 20 to 60, what happens is the average cost goes up by $8.23. On the other hand, if we have little d equals 50, and we move little s from 20 to 60, the average cost goes up by $28.72. And let's see what is. Notice, by the way, that those lines are not parallel to each other, indicating an interaction. It follows from figure 6 that both S and D do have a significant effect on average cost per month. However, the actual numerical change in the average cost due to change in little s depends on the level of little d and vice versa. Because of the interaction, you cannot just talk about, if I change little s, what impact does it have on d? You have to talk about the level of d. Okay, we're now going to go to a second example. Both of these examples and everything I've talked about now can be found in the 12th chapter of my book, Simulation, Modeling, and Analysis. And so here we have a little factory which has a machine and an inspector. And customers arrive over here. They may need to wait in queue. And we'll assume that inter-arrival times are distributed as an exponential with mean of 1 minute. So on average, customers arrive 1 a minute. And then over here, customers are going to have a processing time where we will assume, for simplicity, not realism, that processing times are uniformly distributed between 0.65 and 0.7 minutes. And by the way, the most important thing you may get out of this talk is that if a quantity is less than or equal to 1, it's singular. Okay. Now, I say that jokingly. In fact, if you look at something like processing times, they will tend to be skewed to the right, have a longer right tail. A job leaves the machine. It's going to come over here to the inspector, where it'll be inspected. We'll assume that inspection times, once again for simplicity, are uniformly distributed on the interval 0.75 to 0.8 minutes. Once a part is inspected, it is good with a probability of 0.9 and leaves the factory, and it is bad with a probability of 0.1. And it'll come back here and join the end of the queue if there is one, and it'll be remachined and re-inspected. And potentially a job could go through the system any number of times. Also, the machine breaks down, and we'll assume that the time to failure is exponentially distributed with a mean of 6 hours or 360 minutes. And when the machine breaks down, an inspector will come, and the repair times, once again for simplicity, are uniformly distributed on the interval 8 to 12 minutes. Altogether, we have 6 sources of randomness. Up here, by the way, where there's 2 outcomes, good or bad, that's called a Bernoulli random variable. It's the simplest possible discrete random variable. Okay, as I said before, we have 6 factors of interest. Their corresponding levels are given in the following table. By the way, in the case of the inventory problem, we had the 2 factors, a little s and a little d. They were both quantitative. Our response here will be average time in system, and I'm not sure I wrote it down. I believe that the run length was something like 160 minutes, and I didn't write that down here explicitly. And our performance measure we're going to be looking at is average time in system of a part. And actually, I did have a warm-up period here as well, but I won't go into all those details. Okay, here's our coding chart. We have 6 factors. Our first one is machining times. We'll take our minus level to be what the company, manufacturing company is currently doing. As we said, uniformly distributed over the interval 0.65 to 0.7 minute. Our plus column we can think of as our proposed configuration, maybe a 10% improvement. We're going to reduce machining times by 10%. So for example, if we took 90% of 0.7 minute, that would be 0.63 minute. If we took 90% of 0.65 minute, that would be 0.85 minute. And we have something similar for inspection times. Currently, it's 0.75 to 0.8. We're going to, in the proposed system, reduce the range by 10 per, each one is going to be reduced by 10%, or to be 90% of its current value. The mean is also reduced by 10%. Times to failure, originally, we're exponential with a mean of 360 minutes. We're going to reduce it by 10%, or excuse me, let's say this. Our proposed system is going to be 10% bigger. 10% of 360 is 36. We add on 36, we get 396. It would seem that 10% bigger is worse, but actually it is potentially an improvement, because if times to failure are bigger, then presumably the system will operate better. In terms of times to repair times, we're going to make them 90% as big, or we're going to reduce them by 10%. So 90%, for example, of 8 is 7.2. And coming down to a probability of a bad part, the as-is system, it's 0.1. We're going to reduce it by 10%, so it's going to go to 0.09. For the first 5 factors, which are quantitative, okay, we're looking at what we hope will be a 10% improvement. And then we have our queue discipline. When jobs are waiting in a queue and the corresponding server becomes available, which one will it take out of the queue next? And kind of the standard that is usually used will be first in, first out. So that's our as-is system. Okay, now this one here, which really requires a little bit more explanation. Assume that when jobs are waiting in the queue, their processing time is known. And you can refer to the book for details. Okay, when the corresponding server becomes available, it will take that job out of the queue that has the smallest service time. Okay, queue discipline is qualitative or categorical. Qualitative factor. And the way my former co-author set this up originally is he's going to use factor 6 to correspond to both queue disciplines. Both queue disciplines are either going to be FIFO, first in, first out, or shortest job first. If you wanted to, you can have 7 factors, where factor 6 would correspond to the machine, and factor 7 would correspond to the inspector. And I would ask you here, I don't know whether anybody can respond or not, looking at the coding chart here, which factor, machining times or inspection times, would you expect, based on these numbers, to have a bigger impact on average time in system? I don't know if anybody can answer. No, yes.
You can
I don't
type
even know if
something in
anybody's still there.
question box if you have a thought on that.
Okay. Anybody have an answer?
Not yet.
Okay. By the way, if you get this wrong, you can't stay for the remaining 130 some slides. Well, the answer is, okay, so the inspection times take longer. If you computed the utilization factor of the inspector, it would be closer to 1 than the utilization factor for the machines. And so the machine.
And
So
I'm seeing
between
some
the
other people
two,
come up with the same guess. So seems to be,
same guess? We
yes,
don't want guesses here. We want scientific answers.
that's true.
So the inspection time is likely to have, if we make the inspector 10% faster, it's likely to reduce average time in system more than reducing inspection times by 10%. Okay, so I'll minimize this for right now, and we will in fact go on to page, and it's not advancing. What happened here? Oh, there we go. So in this case here, when this was originally done many years ago, and by the way, we're going to have a full 2 to the 6th power factorial design. Each of the 6 factors are going to be run at 2 levels. So it's 2 times 2, 6 of them multiplied together. We get 64 design points. We're going to make 5 replicates at each of them. This simulation runs very quickly. So we have a total of 320 simulation runs that were made. And here we're going to not use Bonferroni because it turns out when you look at main effects and interaction effects, we're actually going to have 21 different confidence intervals. And if we compensated using Bonferroni, each of them would have to be at a level greater than 99.5%, and they would be huge because of the large T critical points. So here we're going to just kind of sweep this multiple comparisons problem under the carpet and just make them all 90%, knowing that some of them may in fact not contain the true mean, even if it should. And we're going to look at the results here in 2 tables, 7 and 8, and also we're going to have a nifty figure here that kind of explains things a little bit more clearly and visually. So here are the numerical results. We see there in column 1 the 6 expected main effects. So capital E of little e sub 1 would be the expected main effect of machining times. And we look at our 90% confidence intervals. The ones that are in red italics are statistically significant. This factor really does have a demonstrable impact on average time in system. And so we see for machining times that the point estimate is minus 0.17 minute. If we reduce machining times by 10%, we would expect average time in system to go down by 0.17 minute. And as predicted by Dave, we see that the point estimate for the expected main effect of inspection times is minus 1.83. So if we reduce inspection times by 10%, on average, the average time in system ought to go down by 1.83 minutes. In fact, we see that the main effect of inspection times dominates the 6 effects. If we look at the qualitative or categorical factor Q discipline, we see first of all that the magnitude is very close to 0, and also it's not statistically significant because the confidence interval does in fact contain 0. It goes from minus 0.06 to plus 0.04. Kind of on the borderline here is the main effect or expected main effect of times to failure. Its magnitude is the smallest among these 5, namely minus well, the magnitude is 0.07, and since the confidence interval doesn't contain 0, it's not statistically significant. Now, if we come over here to this picture here, what we have here on the vertical axis are all the effects. These are the 6 main effects. The interaction effects we haven't got to yet. There are 15 of them. There's 6 effects, and we're going to take take 2. The number of combinations of 6 things taken 2 at a time will be 15. And on this axis here, we have effect on average time in system. And this line is at height 0, which means there would be no effect. And here, for example, we see our confidence interval for the expected main effect of inspection times. This here is the lower confidence interval endpoint, and that's the upper confidence interval endpoint. And since it doesn't contain 0, that means that the mean effect of inspection times is statistically significant. If we look at factor 1, which is machining times, the confidence interval is smaller. It doesn't contain 0. So machining times does have some effect, as does repair times and also quality, the probability of a bad part. We see that for factor 3 times the failure, it contains 0, and factor 6, it contains 0. Not statistically significant. If we go back here to this table, here we see 90% confidence intervals for the expected interaction effects in minutes. And the ones in red are based on 5 replicates. The ones in red are statistically significant. The ones in black, not italics, are not statistically significant. There's only 4 that are statistically significant. The largest in magnitude is the 2x5 interaction, and that is inspection times and quality. Since inspection times have the largest main effect, it is not shocking that it might have an interaction effect that's non-zero. And if we come over here, once again, and it's a little bit hard to tell visually which ones contain 0, which ones don't. So, for example, where's the pointer? Right there. That one there, it's not clear whether it contains 0 or not, but in fact, it is statistically significant. I guess right now we're at 11:06. By the way, for a while, I was losing my pointer. If I did, the rest of this talk would be pointless. So it's a good thing I found it, right? Okay, conclusions. The greatest improvement in average time in system, namely 1.83 minutes, can be obtained by reducing inspection times by 10%. A smaller amount of improvement can be obtained by reducing machining times, factor 1, reducing repair times, factor 4, and by improving quality from 0.1 down to 0.05, factor 5. The effect of machine times to failure, factor 3, is not statistically significant, and this factor possibly could be eliminated from future analysis. In other words, if you're going to do more experiments, you might just set factor 3 at its nominal level, which was the mean of 360. Keep in mind, though, that statistical significance is not what it's cracked up to be. I had 5 replications here. If I made enough, the half-length of the confidence interval would shrink and shrink and shrink, and eventually, times to failure, the mean effect would probably turn out to be statistically significant. The effect of Q-discipline factor 6 is not statistically significant, and this factor can demonstrably be eliminated from future analysis, which means that if we did additional experiments, we would just set the Q discipline to FIFO, not to be confused with FIDO. By the way, I might throw in another statistical joke here. The greatest application of the normal distribution is writing statistics books. The interaction effects are not statistically significant, 11 out of 15, or are small in magnitude. Even the 2x5 interaction, which was 0.1 minute, represents a change in average time in system of only 6 seconds. The importance in practice, the importance of a factor depends not only on the magnitude of its effect, but also what the cost would be in practice of changing that factor in the actual system. The sample variances, let's see how good we do here in terms of homogeneity of variances, the standard assumption in classical statistics. The sample variances for design points 1. Design point 1 is all factors at their minus level, and design point 16, all factors at the plus levels. The sample variances are 0.4 and 0.03 roughly, which is their factor of 12 difference. Actually, if you look a little more carefully, and I didn't do this in the book, you can get a factor of 16 difference in terms of the variances. Definitely not homogeneous. And actually, I have another example which I really like. It's a predator-prey example, which is not in the book right now. And if you look at the sample variances, there's an 80,000 to 1, a mind-numbing 80,000 to 1 difference in variances. So clearly, homogeneity of variances will not, in general, be true for most simulation models. And since the interactions are not statistically significant or pretty small magnitude, a mean effect here, not in the inventory problem, can be regarded as the change in average time in system that results from moving the corresponding factor from its minus level to its plus level. Okay, summary of factor screening. This is about where I expected to be after an hour. So it's taken a little bit longer. Have to get rid of the statistical jokes. Okay, we have looked at only main full factorial designs, excuse me. Now let's suppose we had 21 different factors that we were interested in. Actually, there was a woman in one of my seminars from Otis Elevator that was simulating elevator operations, and she had 21 factors. And if you did a full factorial design, you would have 2 to the 21 design points, which would be more than 2 million design points, and you'd have to replicate each of them, probably impossible. But there is what's called a fractional factorial design, which I abbreviate as FFD, and it turns out that you can get by with a 2 to the 21 minus 12, which is equal to 2 to the 9th, which is 512 design points, as compared to the incredible 2 million that would be required by a full factorial design. And she said that 512 would actually be affordable. Actually, if you look at something slightly more advanced, you can get it down to about, I think, 225 design points. Now, these full factorial designs can't give you things like 3-factor interactions and higher, but they can give you free and clear estimates of main effects and 2-factor interactions. The assumption of equal variance is not in general valid. Now, if you pick up a design of experiments textbook, I'm talking about something like Montgomery's book, Design Analysis of Experiments, it will often say something like sparsity of effects. In most problems, only a few of the factors are really important. In simulation, it seems that, well, the majority of the factors turn out to be important. Also, in practice, the response surface is not going to be linear. It might be quite complex and nonlinear, as we will see in a minute or two. And the last thing here, which is not written down, the one-factor time approach is widely used, even by people that might have been doing design of experiments for years. And this is not, in general, the right thing to do because many real-world problems or simulation models will have interactions. And now we will go to, okay, change. Why isn't it? There we go. It wouldn't change for some reason. Okay, this here is kind of new. I actually did it yesterday. It's about 9 pages long if we have time. Unbelievably, it took about half a day to do it, though. We're going to talk a little bit about meta-modeling or developing response surfaces, and I think you might find this interesting, even though we can only touch on it here. So very often design of experiments in general or in simulation model in particular, we may want to develop a meta-model. What does meta-model mean? Okay, we have a simulation model. This is a simplified model of the simulation model. Running the simulation model for some models might take a long time just to make one replicate of one design point. If we can develop a simplified model of how the simulation maps the input variables or input factors to the output response, and this is going to, if this is simple and reasonably valid, then we can use the surrogate model to get an idea what would happen for different values of the factors or input variables. And so we can use this to predict the model response for system configurations or factor levels that were not actually simulated. Or we might be able to use this as a vehicle for determining what values of the factor levels can maximize or minimize some objective function or response. Okay, example 4 here. Previously we'd gone up to 3. This is once again a continuation of the inventory model of examples 1 and 2. One of the things that's nice about this here is the inventory model has just 2 factors, S and D, so we can visualize it. Now a meta model will typically be quadratic. It'll have second order terms and take the following form. Here we have the response from the simulation for particular values of little s and little d. R will be a random variable, and we're interested in its expected or mean response, and we're going to write it in terms of a regression equation. This is a constant. It's the intercept of a plane. This term here is going to correspond to the main effect of little s, the main effect of little d. This term here is going to correspond to an interaction between their factors, little s and little d. And then here we have quadratic terms in little s and little d. Quadratic or second order. These betas of j's are constants or coefficients, and we will estimate them from, we will run our simulation at certain design points, we will get response data, and then we'll use regression analysis to estimate those beta j coefficients. Now, one of the main statistical packages out there, which you may have heard of, is called JUMP. It's related to SAS. The SAS Institute, which is actually a $2 billion company, has statistical products called SAS, which is enterprise-wise, and it has like a single user product called JUMP. And actually, design expert, or excuse me, nothing wrong with that. Actually, ExtendSim has some design of experiments capability and interfaces with JUMP. So this is something here that may be new to many of you. We're going to use the JUMP statistical package to generate the design matrix for what's called the Latin hypercube design. Now, if you read kind of the standard run-of-the-mill design of experiments book, you're not going to hear probably much about Latin hypercube designs. These have not been typically used for physical experiments like in a factory, or laboratory experiments, or agricultural experiments. These were designed originally for deterministic computer experiments. And I'm not going to be able to explain this in too much detail. We're going to develop, or we're going to use JUMP to generate a Latin hypercube design that has 20 design points. We have 2 factors, little s and little d, and it's generally recommended that you're going to have 10 times the number of factor design points. And these here I plot in figure 9 on the next page. here we see a coordinate system which has little s on this axis, little d in this package, not package, axis. And this axis goes from 20 to 60, which it did originally. This one goes from 10 to 50. And you see these 20 points randomly sprinkled in there, which are generated from the Latin hypercube design. And this will be done for you by jump. And something I just added this morning here to give you an idea where these points come from. Let's look at little s here. And we want 20 design points. And we want them to go from 20 to 60. We're going to have 20 different levels, and we want them to be equally spaced. So what we would start out by doing is we would first in our column of numbers have 20. Then our next number would be a value such that once again these 20 numbers are going to be equally spaced. Then we'd have a number that's a little bigger. Once again, all these values are going to have equal distances between them. And then we're going to randomly permute these 20 values, which started out at 20 and went up to 60. We're going to randomly permute them, and we end up with now these 20 values in the order given. You see that the value 60 is still there, but it's the fourth in the list. And now you see the values 20 is there, which is the second last in the list. Now we're going to do something with similar with D. We're going to start out with 10, and we're going to list them going up to 50. We're going to have 20 numbers that are going to be equally spaced, and then we're going to permute those 20 numbers independently of what we did for the S column. And what we end up with is these two columns of numbers. And if you check those values out, those two columns of numbers correspond to the points in our figure. Like 24.2, which is probably this one here, and then the D value is 22.6. So that point there probably corresponds to the first row of that table. And okay, what I said here, I didn't really go through the whole thing, excuse me. I'm right there. Now for each of those 20 design points, I made 20 independent replications of the inventory simulation for each of the M equal 20 design points. Now the fact that we have two 20s here, two times we have a value of 20. Don't let that confuse you. Those 20s have nothing to do with, I didn't have time to change it. So we have one thing, which is the number of design points, and then we could have conceivably any number of replicates at each of those design points. So we made 20 replications at each of those 20 design points, and we averaged across the replication. So at a particular design point, we made 20 replicates. We get a response value for each of the 20 replicates. We take the average. Then these 20 averages were used as the response data to obtain the following fitted quadratic regression model. Okay, this is our meta model right here. The fact that there's a hat on there, that means estimated. So our estimated or fitted response value is given by this here. That's the same quadratic equation as before, but now the 6 coefficients have been estimated from our response data. And if we plot this meta model given by equation 2 in figure 10, and by the way, I'm using to plot this what's called the Design Expert software, which you can do a search on. And if you're kind of a beginner, this is really neat software. You can get a 45-day free trial that you can download, and it's really easy to use. So you can play around with design of experiments. And this plot we're going to look at here is called the response surface. And there we have it, a three-dimensional surface. Here's S, here's D, and on the vertical axis we see average cost. And you can see that you're not getting just a flat plane here, which you would if every term was, let's say, well, I won't go into a little detail. If you had every term just to the first order, you would have, quote, a plane. But here we see that it is quadratic because of the S squared and the D squared terms. Now here is a potential meta model that we could use to predict the response or average cost for other values of little d that we didn't actually simulate. If we had a simulation that was very expensive to run It would be nice to have this surrogate model that we could use to predict the response for other values of S and D. But before we actually use it, we should really validate it. And to determine its general predictive ability rather than just being a good model for the 20 design points that we actually ran the simulation for. And what I decided to do to validate it, let's come over here for a minute. To validate the meta model given by equation 2, I looked at two new design points that were not simulated before. Little s equals 50 and little d equals 40, and little s equals 40 and little d equals 20. And if we come back and look at this here, 50, 40 is that point right up there, and then the other one was 20, 30, or 30, 20, which would be that point right there. So I ran new simulations at that point and that one right there. And I made 20 replicates of each, and what I got was average responses across the 20 replicates at those two design points of $132.74 and $119.02. And how good is our meta model going to do? Well, I can go back to our meta model, and I could plug in, for example, little s equals 50 and little d equals 40, and I'd get an r hat value. And what that comes out to be is $134.51. And that differs from what we actually got from running the simulation by a mere 1.33%. And if we ran our simulation at the 30-20, okay, excuse me, not run the simulation. If we plug 30-20, let me just make sure I got that correctly. If we plug 30-20 into our meta model, we get $122.23, which differs from the simulated value by 2.7%, both of which are small errors. Let me clarify or elaborate what I did. I took these new design points, such as 50-40, that I had not run the simulation model at before. I ran it for 20 replicates, took the average value of the response. That should give you some idea what the response surface really will look like for that new design point. Then I took my second order meta model, I put in 50-40, it gives me an R hat, the predicted response. I compare the predicted response with the average response from running the simulation. I got 1.3%, and then for the second design point I got 2.7. And so now I will say the model has been validated in quotes. Okay, probably you should validate it against more new design points, but assuming you have a reasonably valid model, you could now use it to predict the expected response for other values of S and D. And fortunately, I have one more slide. Actually, before I get to that, let me minimize this, hopefully, and come over here to, okay, this is a slide from Design Expert. This is called a contour plot. Here we have little s, here we have little d. And what this curve, right, well, let's take that one right there. That's a contour. What that means is that for any value of little s and little d that falls in that contour, you can expect an average cost of about $130. For any value of little s and d that corresponds to this contour, we would get an average cost of $120. If you came over here and you predict what the average cost will be, it'll be about $118.56. If I actually did an optimization here, and there is an optimization package built into Design Expert, if I take my second order meta model and I search over all values of little s and d for that pair that gives me the minimum average cost, it comes out about $118. Well, it comes out to be 20 for little s and 38 for little d, and the average cost is $118.56. So once again, little s equal 20 and little d about 38 will actually give you the minimum cost over this response surface. And then lastly, and I guess I want to go back here now to coming back here. Okay, the references are, the best book on design of experiments that I know of by far is Design Analysis of Experiments by Montgomery. Now it says 2013. It's actually out. It turns out if a book comes out in February or later of a year, it can have next year's copyright. And there's the reference to my book, which doesn't have the Latin hypercube designs, but pretty much everything else is there. And if I could get one minuscule amount of advertising in, I am doing a 3-day seminar on this topic on November 27 to 29 in the Washington, D.C. area. And you can go to my website. You can get information. And I thank you very much. We still have 40 seconds for questions.
Okay, Averill, and I do recommend that seminar. I did take it a couple of years ago, and that was the foundation for quite a bit of the work that we did with our scenario manager in ExtendSim. As a note, I do have these models that Averill talked about in ExtendSim. I'd be happy to provide them to anyone who's interested. I think I'll try to bundle them with the recorded webinar when we post that. I do have a question that came up a little earlier from Larry Philbin, which is, with the built-in simulation tools such as optimizers and sensitivity and analyzers, what is the role of experimental design now?
Okay, you're saying, for example, that ExtendSim has an optimizer, and how would the use of design of experiments compare with, for example, the use of the optimizer? Yeah,
and it's not even talking. He's not talking about ExtendSim in general. There's various optimizers out there.
In general.
Yeah.
Yeah, like there's something called OpQuest, for example.
Right. Yes.
Okay. Well, first of all, I have to say hello to Larry Philbin because I knew him years and years and years ago. It's nice to see him resurface. Okay. As far as your question goes, if nothing else, you could use design of experiments to determine what factors are the most important or are important. And then if you went on to try to do an optimization, in your optimization you would only basically search over the important factors, which would reduce the size of your search space, and presumably you would get a better answer. Optimizers have several problems in general. First of all, if you have a simulation that runs, any reasonable amount of time, to run an optimizer for thousands and thousands of scenarios, might be prohibitive. And one other thing that I think is the most telling comment is that most real problems don't fall in the problem formulation of optimization, which is that you have an objective function that you want to minimize or maximize subject to constraints. In the past, I actually was involved with about 50 simulation projects, and actually I had a certain person that built the models and everything, and regrettably he passed away in 2005, and maybe a year before he died I said, how many of these 50 simulation projects we did would have lended themselves to optimization? And he said 0. In most real-world problems, you might have something like an existing system and a few proposed systems, and you want to compare them to see which one is the best. The idea that for each factor or each input variable that you want to vary each of them over some range and do this all simultaneously, this just doesn't really occur in most real-world problems. Matter of fact, when I wrote the 4th edition of the book and let's say, improve the discussion of optimization, I went out looking for papers that had been written on the use of optimizers, and I was really hard-pressed to find any, and most of them were studies that were done by professors in universities, so may or may not have represented, real industrial strength simulations. Anyway, so that's my short answer, my long answer to a short question.
Thank you, Averill. There is another question, and that is that...
I thought our contract said there would be only one question, and I've been an extra $500 for each one beyond that.
This is Rene Alvarez. To obtain a response R, how many runs are needed? And I think that's
I'm sorry,
a whole
I didn't
other
hear you.
talk, isn't it?
I'm sorry, what's the question?
The question is to obtain response R, how many runs are needed?
Okay, well, the R, as I used it, is the response from running your simulation one time for each of the values of the factors of interest. And you're going to run your simulation for many different factor levels or design points in order to actually compute main effects and interaction effects. And the recommendation would be that you're going to need multiple replicates at each design point. So that woman at Otis Elevator, assuming that had 21 factors, assuming she made around 500 design points and she had 10 replicates at each, she would in fact have to be making 5,000 replicates of her simulation model. Now that's kind of an extreme case. I don't think in practice most people are going to be looking at 21 factors.
Well,
by the way, in terms of research that's been done on design of experiments for simulation, there haven't been that many people. One person is Jack Kleinen, who's written a book, who's in the Netherlands. His last name is K-L-E-I-J-N-E-N. And the other two main people are Susan Sanchez and Thomas Lucas in the Operations Research Department at Naval Postgraduate School. And you could do a search on the Seed Center at Naval Postgraduate School, and they have a listing of their papers and so forth. I don't know if I answered the question, but that's what my attempt was.
Oh, and Renee responded with a thanks and a note from Averill, who said that your help on his thesis was great. They actually implemented his research at FedEx for maintenance scheduling. So that sounds like some good feedback.
Thank you.
I don't see any other questions. I'll give it just one more moment. If someone else has something, type it in the question box. If not, thank you very much, Averill. As always, this was a insightful view into simulation, and I would certainly recommend taking the full seminar where you can really have time to absorb all the information presented here. And as I said, if anyone's interested, I do have the simulation models that correspond to the two examples presented here in ExtendSim, and would be happy to send them to anyone who's interested. I'll try to see
this talk will be posted, this talk will be posted on ExtendSim's website.
Yes.
So you will be able to get it also. Okay, thank you very much for the opportunity to talk today.
Okay, thank you, Averill.